Welcome to lecture 4.2.2, so it's the second half of the section 4.2 lecture, and this has to do with the nucleus of the atom, and in particular the Rutherford model. And this is an important enough chapter, section, or even part of the section that it merits its own lecture. In 1911, Ernest Rutherford interpreted data from a couple other scientists, and he discovered the nature of the nucleus using a gold foil experiment. And first, he bombarded gold foil with alpha particles, and an alpha particle, we'll tell you right now, is a high-speed helium nucleus. Okay, an alpha particle is a high-speed helium nucleus, which means that particles are high-speed helium nuclei. You do not say nucleuses if you're referring to more than one nucleus. It is nuclei, and these nuclei have lost their electrons around them. This is also called the alpha scattering experiment, and this is what it looked like. He set it up like this, where there was a gold foil, where we had gold foil in the middle of a detecting screen. This was a phosphorescent. This is a phosphorescent. This is a phosphorescent screen around the gold foil, and it would light up whenever a particle would hit it. And then over here in a lead container with a hole in the lead container, there was an alpha particle emitter. It was uranium at the time, and he knew that it emitted these alpha particles. He aimed the box so that the alpha particles would shoot through a slit in the phosphorescent screen and bombard the gold foil. They wanted a narrow slit because anything that would bounce back they wanted to be able to capture on the screen. Now what he anticipated seeing was a whole bunch of these particles, according to the Thomson model. You'd see a whole bunch of particles right in through here, because with the Thomson model, that's ugly. With the Thomson plum pudding model, the atom would have to be loose enough that it would have to be loose enough that if we fired alpha particles at it, they would have so much energy that they would just shoot right through. And there would be some sort of deflection side to side because of the negatively charged electrons shooting past, the positively charged alpha particles shooting past the negatively charged electrons. And so there would be a little bit of deviation on either side of the main path. However, what they found were these particles that were actually deflecting over here, and there was some over here, some over here, and even some that would deflect way backwards in here and then back this way along these lines. And this was actually a remarkable discovery. Because of these guys over here, and to some degree this over here, that not only did there have to be something so dense that there must be a dense part to the atom. Okay. It would also, because of these deflections off to the side, it would also have to be positively charged because of the major deflections it was getting without actually hitting it. So there must be a dense part of the atom, and it must be positively charged. Which led Rutherford to him coming up with this particular theory of the atom, where you would have these alpha particles charging through, and the vast majority of them, majority of alpha rays, would be just passing through what would be the area of the most of the atom, just pass right through. However, a very few, and this is an important thing, not just a few, not just some, but a very few is key here. That a very few would pass by the nucleus and get deflected away. Some would pass by the nucleus and get deflected away. And then some would come through and bounce right off. And through this data, he came up with this model of the atom, that there would be a dense, positively charged center of the atom. And around it would be Thomson's electrons, as if it was in the plum pudding model, except these are now orbiting the nucleus. Somehow they would just be around, attracted to the nucleus due to its the positive to negative attraction. And so once again, we compare the Thomson model to the Rutherford model. Notice the Thomson model had these had the electrons embedded in a goop of positive charge. Well, Thomson's model drastically reduced the size of the material that had the positive charge to just that was in the center of the nucleus. And then through the area where the electrons were, okay, and the electrons were still scattered throughout, we'll have these negative charges in here. Okay, these negative charges would still be in the atom, but then we would have our alpha particles streaming through. They'd come in here, and then they'd bounce off, and they'd have more coming through this way and coming through that way, and they'd be passing through the atom. Only when they came close to the nucleus would they be deflecting away. And so the fact that there were very few, so let's go over this for a minute here. The fact that there were very few alpha particles that were colliding or veering off far from their original path meant that the nucleus was very small. But we also knew that it also contained almost all of the mass. Which meant that it was also very dense. It was very small, and all the mass meant it was a very dense material that was strong enough to withstand the punishment of a alpha particle coming in, hitting the nucleus, and then bouncing away. So once we discovered the nucleus, Rutherford posited his nuclear model of the atom. And it starts with this. The atom is mostly empty space. It's mostly empty space and is composed of a tiny nucleus, which is the core of the atom, and it is composed of protons and neutrons. Now, actually, at the time, he didn't really have protons and neutrons in mind, because he didn't know what they were. But he just knew that there was a positively charged nucleus, and he said that they were composed of nucleons. And we discovered later that the nucleons were both protons and neutrons. Okay, we also found that the nucleus is much smaller when it's compared to the whole atom, yet it contains almost all of the mass. The nucleus has a net positive charge, and the electrons moving around the nucleus make up most of the atom's volume. Okay, and so a ratio here, if 1 kilometer represented the diameter of the atom, then a dime would be the size of its nucleus. So a dime is not much more than a centimeter across. Okay, and so it would be 100,000 times smaller than the size of the nucleus, which you can tell then the very few of the data of the particles that bounced back truly was very few. It was much, much less than 1%. But the fact that it did happen meant that there had to be something there, and that it had to be very, very small. Now, we have since learned that protons and neutrons are made up of even smaller particles called quarks. And 3 quarks combine to make up protons or neutrons. Protons and neutrons make up the nucleus. They are held together by the strong nuclear force that overcomes the mutual repulsion between protons, because like charges repel each other and opposites attract. So think for a moment. Inside this really teeny tiny cramped space, we have this nucleus, and you can see that, let's say the red things are, or the blue things are, no, the red things are protons, and the blue things are neutrons. If all you have, mind you, in this teeny tiny cramped space, all you have are these red positively charged things and the blue neutrally charged things. These guys are awfully close to each other to all be positively charged. And due to the electrostatic repulsion, of the like charges of the protons, there needs to be something to overcome that in order to keep the nucleus together. And there's 2 things at play here. One is the neutrons. Okay, these neutrons were discovered later, but these are spacers in between the protons that will give the proton space. It increases the distance between each proton, which decreases the force of them repelling each other. So these are nuclear spacers. Okay. Then there's the strong nuclear force. No, not Sunday Night Football. The strong nuclear force, which is a subatomic force that holds the protons and neutrons and everything inside the nucleus together, just because they are close together. They are close together on a nuclear scale, which allows the strong nuclear force to take over. The other issue with the Rutherford model is this. And so we'll move this out of the way, and we'll hide these. The other issue with it looks like this. And in the planetary model of the atom, if this is our nucleus and we have electrons going around the nucleus, if that's it, then the electrons should be losing energy as they are changing direction. If their velocity is this way, then they're going to have a changing direction that's going to be constantly changing into that direction. It will always be towards the nucleus. But if it's moving that way and it's changing in that direction, it will consistently spiral down until it hits the nucleus. And so all of the energy should be gone, and all the kinetic energy electrons should be gone, and the electron should crash into the nucleus, and the planetary model should collapse. So there needed to be a new version of it, and the new version will come in Chapter 5, when we learn about the Bohr model of the atom. Or actually, no, it'll come in the next section, when we learn about the Bohr model of the atom. So, that's it for 4.2.2, and we'll see you guys next time.